Hi, in this video we are going to talk about the so-called Splay trees, so let's get started. So far we have been talking about binary search trees, and we come to the conclusion that we have to make sure that these binary search trees are balanced if we want to make sure that the logarithmic time complexity is preserved. So we come to the AVL trees and red-black trees. And then we pose the question that can we do better? And yes, maybe with the help of Splay trees we could do better. And this Splay tree is the most popular data structure in the industry. So it is kind of a binary search tree. Most of the operations have logarithmic time complexity as well as for AVL trees or red-black trees, but some are very slow, even for example linear time complexity. So unlike AVL trees, a Splay tree is not strictly balanced, and that's why it is faster, because we don't have to bother about keep rebalancing it each time we insert or make any operations on it. And it is very easy to implement. So the most popular data structure in the industry, as I said earlier. And why is it good? Why is it so popular? Because it guarantees fast access to elements that has accessed recently. And that's why, for example, caches relies heavily on these data structures, because that's why we use caches. We want to reuse the items we have used in the past seconds, for example. And with the help of Splay trees, we can implement this problem very easily. So Splay trees are kept balanced with the help of rotations. It is kind of the rotations we have been familiar with AVL trees. So, for example, we have this situation, and for example, in the first tree, there's a root node y, and it has a left child x. And if you want to make a right rotation, then the x will be the root, and the x right child will be the y. And of course it is symmetric, so we can make the rotation on the opposite direction. So if the root is the x and we want to make sure that in the new tree the root will be y, then we have to make a left rotation. So we just have to update the references, which can be done in approximately constant time complexity. And that's why it is very fast making these kinds of rotations. And it's very important that the properties of a tree, a binary search tree or a Splay tree, so the properties of the tree is not going to change. For example, the maximum item, the minimum item is going to be the same no matter how many rotations we make. And the in-order traversal is the same. For example, on the left tree, the in-order traversal will give us A, X, B, Y, C. And after making the right rotation, if we make an in-order traversal on the right tree, A, X, B, Y, C, it is the same. So the properties of a tree are not going to change because of the rotations. And the most important operation for a Splay tree is the find or search operation, because finding the minimum, the maximum, the in-order traversal, and all the other operations are exactly the same as for AVL trees and exactly the same as for binary search trees. So it is like a standard binary search operation. We have to make rotations when we find a given element we are looking for. It is going to be the root node, so that's what we call splaying, and that's why this data structure is called Splay trees. So we just insert the given node according to the binary search tree operation. Then we make rotation in order to be to make sure that this node we are looking for is going to be the root node after the rotations. And why is it good? Why are we bothering about it? Because in the next search it can be accessed very fast, even in constant time complexity. Because with the help of splaying, the new root will be this node. And if we start each operation at the root node, so that will be the one we are looking for. So this is why it's very important for splay trees that every item we have searched for is going to be the root because of the splaying method. So there are 3 ways we can make it happen. I mean, there are 3 ways we can make sure that the node is going to be the root. There's a zigzag situation, the zigzag situation, and a zig situation. So what about the zigzag situation? In this situation, the given node X, for example, is a right child of a left child, or the given node X is a left child of a right child. Because I'm a physicist, I think that symmetry, even in nature or whatever, these data structures are very important, and we can come to the conclusion that in this symmetry, because it's kind of a symmetric structure, right child of a left child or a left child of a right child, we have to make every step exactly the same. I mean, we just have to make sure that we make the right decisions accordingly. So for example, here in this situation we have so the y is the root node and the z is the left node of the y and the x is the right child of the z. So the x is a left-right. This is the left-right situation. So as we have discussed, we have to apply the zigzag case or the zigzag method whenever the given node x is a right child of a left child. And here the x is the right child of a left child, because the right child of z is the x and the left child is y is the z. So this is the x is the right child of a left child. And of course I'm going to denote the subtrees with the help of these triangles. So for example, the A subtree may consist of several other nodes, for example the K, the E, the D, whatever. So we have to rotate node X to the left. And after, as we have seen, it's quite the same operation, I mean these as far as these rotations are concerned, as we have discussed in ADL trees. So we just have to rotate to the left, then the x will be the left child of y and the z will become the left child of x. And of course we have to update the subtrees accordingly. It is not good. Why? Because we want to be the node x to be the root, and the x in this situation is not the root. So we are in this situation and we have to rotate the node x to the right. So, and after this rotation, the x will be the root node, and this is the case we are looking for. So we have to make a left and then we have to make a right rotation. And exactly the same appeared when we were dealing with ADL trees. Then we have the zigzag situation, when the given node x is left child of a left child, or the given node x is a right child of a right child. It is quite symmetric. So as I said earlier, here we have discussed when we are dealing with a right child of a left child. But if we would be dealing with a right child, I mean the left child of a right child, we would have to make the same rotations but on the opposite directions. So I think it is quite intuitive. And let's see an example of the zigzag situation. So this is a typical zigzag situation. The x is the left child of z and the z is the left child of the y. So the x is a left child of a left child. So we have to rotate node z to the right, not the x. It is very important that we do not start with the node x. We start with the parent of the node x. And we make a right rotation on z. Then the parent of the x will become the root, because the parent of the x is the z. And after the rotation, the z is the root, as you can see. It is not good. Why? Because we want to be the node x to be the root. So we have to make another rotation to the right. And that will be the solution. And of course we have to update the references to the subtrees accordingly. So these A, B, C, and D subtree have to be updated. We just have to change the references, and that's why it is a very fast operation. And the third step is the zig situation. So we have to repeat the previous two steps, the zigzag and the zig-zig situation or zig-zag case, over and over again until we get to the root. And sometimes we end up at the left or right child of the root, and we just have to make a single right or left rotations accordingly without zig-zag and zigzag situation, just a single left or right rotation. So in this zig situation, so here x is just the child of the root. And for example, if x is the left child of y, we just have to make a simple right rotation, and as you can see, this with the half of this rotation, the x will be the root. So we just have to make a single right rotation. If the x is the right child of the root, then we have to make a left rotation. So for example, we have a binary search tree like this, and it is exactly the same as a binary search tree. We want to search for 12. The searching operation is exactly the same as for binary search trees. We start at the root. We come to the conclusion that 12, the number we are looking for, is less than the root, so we go to the left subtree. The 12 is greater than the given node, so we go to the right subtree. Then 12 is less than 19, so we go to the left. It's less than 16, so we go to the left. And this is the node we are looking for. So we have managed to find what we are looking for, but this is a splay tree, so we have to make the splaying on every search. And why is it good? Because with the help of the splaying, this 12 node will become the root node, and whenever we want to find the 12 again, it is not going to take logarithmic time complexity, it is going to take constant time complexity, which is very fast, and that's why caches and very fast databases, for example, relies heavily on not a binary search tree, but on a splay tree. Because if we would use a binary search tree, we would not make any rotations, and whenever we want to find, for example, this 12, we have to go to the left, then the right, then the left, and left again. So we have to make operations, but with the help of splaying, we don't have to make any comparisons. We know that the 12 will be the root node. So, yeah, it is a splay tree, as I said earlier, and we want to make the splaying to make sure that the next time or search for 12 operation will be faster. So this is a zigzag situation. So if we want to make sure that the 12 node will be the root, we have to come to the conclusion that this is a zigzag situation. So we have to make a right rotation and a right rotation again. Then this is a zigzag situation, not a zigzag as earlier. It is a zigzag situation. So we have to make a left rotation on the parent node of the x, and here x is 12, the parent of x is 10, so we have to rotate 10 to the left. And of course update the subtrees accordingly. The subtrees here are the 1 and the 16 and 19. Then the root node is not the 12, so we have to make again a right rotation, and it is going to be, now our splaying is fine, because we were searching for 12, and after the splaying, the root node is the 12. So why is it good? Because if we want to find again 12, it's going to be the root node. So we can get it, we have found it in constant time complexity because it is the root node. So this is why splaying is important. So what about inserting or insertion into a splay tree? It is exactly the same as insertion into a binary search tree, but sometimes we splay the inserted node to the root, as we have seen for searching or if you want to find anything, but not always. I have seen some implementation where we use the splaying only and only if we want to find or search for something, but on the other hand, there are some implementations of splay trees where we have to or not have to, but we make the splaying on insertion 2. So we keep inserting stuff in the same manner as for binary search trees, and we keep splaying the inserted node to the root. And sometimes it's proved to be very important, because after the insertion, maybe there's a high chance, a high probability that we are going to search for that node, and because we have splayed the tree, that node will be the root node, and we can find it in constant time complexity. So this is why, and to be summarized again, but I don't want to repeat myself again and again, but this is the main difference between binary search trees and or balanced binary search trees and splay trees, that if we want to search for something several times in a binary search tree, we have to it's going to cost the same, because we do not change the structure of the binary search tree. And that's the heuristic, or although it's not quite a big heuristic, but that's the heuristic for splay trees, that we make sure that the node we are looking for is going to be the root node. So we reconstruct our tree in order to give a chance that the searching operation will have constant time complexity instead of linear time complexity. So that's all about splay trees. Thanks for watching.